Can you guys see my screen?
Yes, sir.
Yes.
Okay. So today we're going to do reading six. Uh, it's on simulation methods in finance and how to model uncertainty. We are also going to implement a technique called as Monte Carlo simulation today to see how it looks in Excel and what could be the applications of the same. Very important technique to model future uncertainties or to model scenarios which probably have never occurred in the historical past. Okay, so we'll look at some applications later on as we go. So this chapter is going to cover concepts related to log normal distributions, Monte Carlo simulation, and bootstrap resampling. We'll first try to understand these terms and then we will implement Monte Carlo simulations. Okay, so the first premise is why asset classes can't be normal, right? So when you look at an asset price and when you look at a normal distribution on the left, can I say an asset price can never fall below zero? An asset value cannot be negative, right? Which is why a normal distribution will not work, because if you look at a normal distribution, there will be values which would be above zero, but there would be certain values which would be below zero. So normal distribution is not appropriate to model prices because prices can never be negative. So then we need to hunt for a distribution which can be used for modeling purposes, which can probably model asset price. So instead of saying that price is normal, which is not possible normally distributed, let's assume that return is normally distributed. If we say that, theoretically it makes sense because there could be values above zero, there could be values below zero. Returns are permitted to have, theoretically, values way above zero, way below zero. So theoretically, it makes sense where returns could be normally distributed. Now, whether that really holds in the real world or not, that's a big question mark. But at least from a modeling perspective, instead of saying prices are normal, we will rather assume returns are normal. And we will work with that assumption. What are the features of a normal distribution? A normal distribution is typically symmetrical and unbounded, allowing for negative values. And most importantly, it will not allow asset prices to fall below zero. Yeah. So it becomes a much more realistic way to model financial assets. So the solution is to model prices with a distribution called as log normal distribution. Now here you can see two distributions. On the left is normal and on the right is a right skewed distribution. It's called as a log normal distribution. So what is the difference between these two? Now if I assume returns to be normally distributed, the prices become log normally distributed. Okay. Uh, how is this possible? Let's look at the theory behind this. So we say that if, say we have two variables y and x, okay, and say y is equal to ln of x. Yeah. Now if we say that this y is equal to ln of x is, if we say is normally distributed, then by theory, x will be log normally distributed. Which is why when we talk about returns, which are normally distributed, now returns we know can be characterized in two formats. One is arithmetic return, the other is compounded returns or log returns. Arithmetic returns look like this: P1 minus P0 divided by P0. And log returns look like this: ln of P1 by P0. So this is a one period return, arithmetic and log returns. The second return which I've written here is assuming continuously compounded returns, which means compounding keeps on happening, where the frequency of compounding is theoretically infinite. So continuously compounded is the basic assumption here. And this is how returns can be put. So here we are saying returns which look like this, the log normal returns. If this is normally distributed, then the price is log normally distributed. Yeah. So which means that the prices, say stock prices or other asset prices, can be assumed to be modeled along a log normal distribution. Yeah. So that's a bit of a backdrop with regards to normal and log normal distribution and the fungibility of returns versus prices. This is very, very important, what I've just discussed. So always remember returns can be can have negative values. So returns will have or can be modeled as normal distribution. And since returns are written as ln of p1 by p0, um, p is log normally distributed or prices are log normally distributed. Yeah, so this is a bit of backdrop on this slide. And when I write R as ln of P1 by P0. And if I take, say, exponential on both sides, I get P1 is equal to P0 into e to the power R. If we extend for t periods, it looks like this. Pt is equal to P0 into e to the power RT. Yeah, just 1 second. Sorry. So essentially what we're saying is Pt is equal to P0 into e to the power RT. And that becomes the price or the future price at time period t. Yeah. So if I'm able to simulate R, I can find the price in the future, which is Pt is equal to P0 into e to the power RT. P0 will be known, T will be known, R can be simulated. And if R can be simulated or if R is known, then the price at time period T will also be known. This, please note, is assuming that returns are normally distributed. So the prices will then follow log normal distribution. Any questions on this so far?
No, sir.
Okay. Now, coming to the foundations or statistical foundations of the log normal model, the biggest advantage of log normal returns is that returns become additive. Okay, let's take a very simple example. So why we say that log returns are additive. So let's consider the return over 2 days, 0 to 1, 1 to 2. Prices are P0, P1, P2. Return, the log normal return over the first period, 0 to 1, can be written as Return 1 is equal to ln p1 by p0, and return 2 over 1 to 2 can be written as ln p2 by p1. Yeah. Can I say if I were to consider returns between 0 to 2, I would have written returns 0 to 2 as ln p2 by p0, right? So ending price divided by original price. Now I can realign this as p2 by p1 into p1 by p0, and then I can separate the two logs because log of a product is equal to the sum of logs, and this we know is nothing but return 0 to 1, and the other is return 1 to 2. Yeah. So return 0 to 2 is nothing but the summation of returns 0 to 1 and returns 1 to 2. We can, in fact, through induction, then go on to prove that return between 0 to n is the summation of returns I minus 1 to I. Yeah. So that's how it looks. So log returns are additive, and that is what is being mentioned here, additive returns. Also, a very key role of central limit theorem that even if short-term prices or returns rather are not perfectly normal, the central limit theorem implies that the sum will be approximately normally distributed. What does that mean? In fact, central limit theorem is an extremely important theorem which is borrowed a lot in finance, and hence a lot of modeling happens on normal distribution, especially assuming returns are normally distributed. These assumptions generally hold true in you know quieter, calm conditions or scenarios. But whenever there's stress in the markets, you should not assume returns are normally distributed. So in stress scenarios, we should consider distributions which are, you know, heavily negatively skewed, ideally, and which have or which are fat-tailed, which means the probability of seeing extreme tail events is higher than what normal distribution suggests, right? So the returns equal to normal distribution, usually for regular situations, regular scenarios, quieter, calm scenarios. But for stress situations, we generally we cannot assume this because returns will not be normally distributed. However, even if returns are not normally distributed over shorter periods, uh, even if that is true, if we keep collecting these returns and we see returns over longer periods, or when the sample size keeps on increasing, the returns might tend towards normal distribution. And that is because of the central limit theorem and the law of large numbers, which basically says that suppose you have a sample which looks like this. The sample is a limited sample. It could have a limited number of sample points, a finite number of sample points. Suppose from this, sorry, this is the population, and suppose you draw samples from this. You draw small samples from this, and you note their mean. Okay, so we note the mean x bar, and we keep redoing this exercise where we simulate a lot of different samples, and at the end of each exercise, we're going to just note what is the sample mean of each selected sample. If we keep doing this infinitely, the PDF or the probability distribution function of this sample mean becomes or tends to a normal distribution. So mu tends towards a normal distribution if the number of samples tends towards infinity or is very large. Yeah, so we keep repeating this experiment. Ultimately, we are going to get a normal distribution. So even if we start with a non-normal distribution, we could end up getting a normal distribution on the sampling mean distribution. And that is because of these properties of normal distribution where you keep on sampling, and over infinite number of samplings, this distribution of sampling mean will tend towards a normal distribution. Yeah. So that's exactly the role of central limit theorem. And that's what we, mean that if we are doing so many simulations, like thousands, lakhs, millions of simulations, then there's validity towards using normal distribution. Okay. So that's the crux of central limit theorem. And that's how it looks. So total return can be modeled as normally distributed. And if you invert that, or rather you take the log of that, you will end up, or you rather look at the price, you will end up getting the price as log normal distribution. So you start with the current price and you want to model uncertainty in the future. And a way to do that is using a simulation approach or a simulation model. Yeah. So all these are basically probabilistic paths that you can see. So a stock price can probably follow this path or this path or this path, and it will give us a range of possibilities in the future. So the question is, how do we do this and how do we generate these paths? So method one is to use the assumption of a distribution and generate futuristic paths based on those assumptions. And that is what is Monte Carlo simulation all about. So Monte Carlo simulation, you're going to specify the model, which means you're going to define the distribution of your asset price. So define asset price distribution, which essentially means that you need to define your asset return evolution, which means how does the asset return evolve. Second is, based on this distribution, you randomize the outcomes and you create random paths or generate random paths. And based on the outputs of the random paths, you analyze the results, create the distribution, and then probably the mean value will probably give you the price of the instrument in the future. You take the present value, that will fetch you the expected price of the instrument today. So this is what generally is done in the industry. So in a lot of places, Monte Carlo simulations is used. We will look at some of the specific examples where this could be used. So Monte Carlo simulation in practice, it's very heavily used to value complex options or derivatives which ideally do not have analytical solutions. For instance, if I want to value a path dependent option, for instance. Okay, so step back, what is a path dependent option? A path dependent option is basically an example of an exotic option which does not fall into the category of your long call, long put, short call, short put, right? It has different features which make it exotic. An example of path dependent option is Asian option. Yeah. So what is an Asian option? In an Asian option, you let the prices evolve over time, and then the option which is based on such an asset will have this characteristic. It will be max of average of STs minus K, comma 0. This will be the payoff function of a long Asian call option. Okay. It looks like max of average, which means it takes the prices at the end of every day, and say at the end of the month, if you were to find or if you were to calculate the payoff, it will take the average of all the realized ending values of the asset on this path, and you take the average of that. So that becomes the average stock price over the entire path minus the strike price, comma 0. So that defines the payoff of a long Asian call. Similarly, payoff of a long Asian put will be max of K minus average of ST, comma 0. So very similar to long call, right? Long call, the payoff we know is ST minus K, comma 0. And for a long put, it's max of K minus ST, comma 0. Long call is similar to buying the asset where the buying rate is fixed at the strike price. Long put is alternative to selling the asset where the selling price is fixed at K initially. So similar to that, we have payoffs of exotic options. Here we've taken the example of an Asian option, right? So this is how the payoff function looks like. Another example is look back option. Yeah. So it will, so suppose this is the path of the asset, and at maturity, the payoff of say look back call option will be equal to the max stock price achieved on the entire path minus K comma 0, which means it will see all the peaks. It will choose the peak, which is the highest, and it will choose that as the price here. Yeah, in the payoff. So this is the example of a look back call option, which takes the maximum or the highest value of the realized uh, asset price over a given period. So how would you simulate the values of these calls or puts exotic options? Today, how will you find the value today? So what we'll have to do is we'll have to simulate various paths, calculate the average payoffs, and then calculate the average of those values and then discount them back today. So that's where Monte Carlo simulations could be used. We'll go through the method very soon. Any questions on this?
No, no, sir.
Okay. All right. So let's go back here. So you need to specify the distribution. So how to put this into practice? Specify the distribution, generate random values, value the option, repeat and aggregate. Okay. So suppose let's take the example of an Asian call option, right? So how will you use Monte Carlo simulations to price this Asian call option? So for that, we have a starting value of the stock. Okay. Now, when we run simulations, this stock can take any path and typically will end up at maturity with the sum ending stock price. Yeah. And that is true for different paths. So in Monte Carlo simulations, you are going to model various kinds of paths. And for every path, we will have to calculate the average stock price, say on path 1. Similarly, average stock price on path 2, and so on and so forth. Once we have that, we feed that into a payoff function. And our payoff function is nothing but average stock price minus K comma 0, max of that. And then you calculate payoffs for each of the paths. Once you calculate the payoffs for each of the paths, you will have to eventually take the average of all these values, and that average will give you the future value of the Asian call option at maturity. But if I say what is the value today, so you need to discount this back or take the present value of that. So present value of the average of all these paths or payoffs is going to give me the price of the option today. So generally, when we take present value, we will use this formula, e to the power minus RT into your average is going to give you the value of the call option today. And this, we are talking about an Asian call option. Yeah, so this is a Monte Carlo simulation in practice. Any questions on this approach? Okay.
Yes, sir.
So let's take a step forward and let's look at some of the applications of Monte Carlo simulations. So Monte Carlo simulations is broadly used in the investment world and the risk world. It is used to value complex securities like options. I've just given you an example of exotic options like Asian options or look back options, where you can use Monte Carlo simulations to value these options. Okay. You can simulate future profits and losses from a trading strategy using Monte Carlo simulations and check if the out of sample in terms of simulations works or not for a particular trading strategy and how robust it is. You can calculate value at risk based on Monte Carlo simulations, and that method of VAR calculation is called as MCS value at risk. So MCS value at risk assumes that the asset price follows a certain distribution. Then we draw from these distributions, simulate the asset price, and then we calculate. We do that across various assets in our portfolio, calculate portfolio returns ultimately. So all these are, say, asset distributions, asset one distributions, asset two distributions. You'll ultimately create portfolio distribution, eventually portfolio return distribution, and then you'll calculate value at risk, which is nothing but the cutoff percentile in the left tail, or the maximum loss given a certain confidence level over a period of time is called as value at risk. So Monte Carlo simulations can be used to generate value at risk figures, especially for those assets wherein you want to generate future scenarios which have never been seen. A classical example of this is, suppose if I ask you, or if I tell you that you have a portfolio of high quality corporate bonds. Yeah. Suppose in this portfolio you have Reliance, you have Adani. Okay. Now, can I say that when I look at the historical prices or historical data of these bonds, first of all, they have never defaulted. So you will never have defaults. Okay, they have always made their payments. They have always made coupon payments on time, right? So there are no defaults in terms of principal or defaults in terms of coupons. But suppose if I tell you to calculate the default risk of my corporate bond portfolio. Now, can I say historically these have never happened? That Reliance or Adani bonds or AAA bonds of currently high quality companies have defaulted. There's no historical precedent for that. So how do we calculate default risk is a big question mark, right? So there we will utilize Monte Carlo simulations approach where we will assume a certain distribution for these corporate bond spreads or prices. After assuming this distribution, we're going to simulate rare events like uh, defaults or like rating downgrades. And then we are going to calculate what is the P&L out of these rare events. And then we are going to create a distribution of these P&Ls. And then the value at risk coming out from such a returns distribution is basically your MCS value at risk. And that's where Monte Carlo simulations is useful. By the way, this approach is popularly used in Basel 2.5 and 3. And this approach in Basel 2.5 and 3 in the regulatory documents is called as IRC, which is incremental risk charge. Okay. So this is not part of CFA, but I thought of giving you a bit of a background on how MCS is useful in terms of VAR. So in Basel 2.5 or 3, there is a component called as IRC, incremental risk charge, which uses Monte Carlo simulation approach in order to calculate value at risk. So here, what kind of risks are we capturing? We are capturing unknown or unseen risks. Like what? Like defaults and rating downgrades. Usually, a lot of times for high quality companies or bonds of high quality companies, there is no historical precedent of seeing defaults or seeing rating downgrades. Yeah, and which means that you would need to simulate such kind of outcomes using Monte Carlo simulation by using certain distributions, calculate P&L, take create the distribution of those P&Ls or returns, and then calculate the Monte Carlo simulation based value at risk. Yeah, so this is how it looks. So that's the application in risk management, and that is what we have written here. Yeah, it is used to simulate pension fund assets and liabilities to analyze funding gaps over time. So your assets and liabilities are going to fluctuate. And the difference between those, it's possible that sometimes the asset can fall below liability, creating a funding gap. So in order to simulate these funding gaps and I'll analyze these over a period of time, especially over stressed events, we could also use Monte Carlo simulations there. And also sometimes Monte Carlo simulations are used to value portfolio of assets which have non-normal return distribution. So there you need to use a fat tail distribution like a Pareto distribution or extreme value theorem or an F distribution or a mixture normal distribution or some other distribution which has fat tails, and that will lead you to, or a T distribution, and that could lead you to valuing assets which have non-normal return distributions. Yeah, so these are some of the applications of Monte Carlo simulations used in the industry. So that's the first method, which is futuristic. So generate futuristic parts. So that's the first point. And the second method, or the second method is using historical data. So there, that method is called as bootstrap resampling. What it does is you basically